Sparse Regression LDPC codes. This is a concatenated code for the additive white Gaussian noise channel, built from two capacity approaching ideas that are usually studied apart. We will construct the code, decode it with approximate message passing, and see why decoding its two parts jointly is what makes it work. Two families of codes motivate this design. Low-density parity check codes are capacity approaching and decode efficiently under belief propagation on their factor graph. Yet at the short to moderate block lengths where spatial coupling is impractical, they leave performance on the table. Sparse regression codes come from the sparse recovery tradition. Under approximate message passing, they reach the Gaussian channel capacity, but they are weak at finite block lengths. A natural fix is to concatenate the two, and earlier work does exactly that. The catch is that those schemes pass information from the inner decoder to the outer decoder only once, in sequence. The question here is sharper. Can the outer code structure be folded directly into the recovery loop, so both codes are decoded together? The construction has three steps. First, the information bits are encoded by a non-binary LDPC code over the finite field f sub q, producing a code word of L symbols. The field size q is a power of 2, and it is chosen to equal the section size of the inner code. Second, each field symbol is indexed to a standard basis vector of length q. The symbol's value selects which single entry equals 1. Stacking the L blocks gives a long vector S that is sparse, with exactly one active entry in each section. Third, this sparse vector is multiplied by a Gaussian design matrix A, and the product is the transmitted signal X. The indexing step is the pivot of the whole design. It turns an algebraic code into a sparse recovery problem, which is precisely what approximate message passing is built to solve. At the receiver, the task is to recover the sparse vector S from the noisy observation Y. Approximate message passing does this by repeating three moves. It forms a residual between the observation and the signal implied by the current estimate. A correction called the Onsager term is added, and it is what keeps the effective noise Gaussian. From that residual, it builds an effective observation, R equals A transpose Z plus the current estimate. A denoiser then maps the effective observation to a cleaner estimate of the sparse vector, and the loop repeats. Because the sparse vector has exactly one active entry per section, a good denoiser should exploit that structure and the parity checks of the outer code as well. The performance of the whole decoder now rests on this single choice. Here is the property that makes everything possible. Under approximate message passing, the effective observation behaves like the true sparse vector seen through independent Gaussian noise, R equals S plus tau times zeta. Taken one section at a time, that is a Gaussian vector channel attached to each LDPC symbol, much like pulse position modulation. So the posterior over a section's field value is a softmax of its effective observation, with a temperature set by the noise variance tau squared. These per-section posteriors are exactly the local observations that belief propagation needs. Placed on the factor graph of the outer LDPC code, they let the parity checks exchange messages and sharpen every belief using the code's redundancy. The dynamic denoiser is this idea. Run a few rounds of belief propagation on the outer graph inside each message passing iteration. The inner and outer codes then share soft information continuously, iteration after iteration, instead of in a single handoff. A decoder is only trustworthy if we can predict its behavior. The denoiser is non-separable. Because belief propagation couples the sections, each section's estimate depends on the whole factor graph, not on its own observation alone. To analyze it, unroll the neighborhood of a variable node into its computation tree. If that tree has no loops, belief propagation on it is exact. On the tree, every message is a smooth function of its inputs, and composing a fixed number of them leaves the denoiser Lipschitz continuous. That Lipschitz property is exactly the condition the framework of Berthier, Montanari, and Guyen requires. With it, state evolution holds rigorously, even though the denoiser is non-separable. State evolution reduces the high-dimensional system to a single scalar, the effective noise variance tau squared, and a recursion that updates it each iteration. When tau squared falls below the belief propagation threshold of the outer code, decoding drives the error towards 0. The paper then goes further. Using the code's geometric uniformity and a link between a message's error and its norm, it derives a low-dimensional surrogate for state evolution. That surrogate predicts performance from the system parameters alone, so a code can be tuned and optimized without long Monte Carlo simulations. Now the evidence. Contrast two denoisers. One increases the belief propagation rounds as the iterations proceed. The other runs none, so the inner and outer codes never share information. Jointly decoding produces a steep waterfall in bit error rate that the disjoint decoder simply never reaches. Compare it against three optimized benchmarks: a SPARC LDPC construction, a binary LDPC code with BPSK, and an LDPC code with 4 PAM bit interleaved modulation. At a bit error rate of 10 to the minus 3, the SR-LDPC code leads them by about 1 decibel, half a decibel, and a tenth of a decibel. And since each channel input is a Gaussian random variable by construction, the scheme captures a shaping gain over the Gaussian channel almost for free. One refinement makes the decoder practical. Running several rounds of belief propagation in every iteration can become computationally costly. The keep graph variant runs just 1 round per iteration, but it preserves the graph messages between iterations instead of resetting them. Reused this way, old messages act like information from deeper in the code's computation tree. This keeps decoding much cheaper, with almost no loss in error rate, and even a small gain at high signal-to-noise ratio. Running belief propagation inside every iteration, so the two codes decode as one, is the idea that carries the whole design.